Swayam Prabha. Digital India. Educated India.
In this lecture, let us discuss about the equilibrium composition of high temperature air. We will discuss about variation of Cv as a function of temperature, and we will also try to impress that you additionally have to mention about pressure. Just defining temperature is not good enough, and we will see the variation of Cv for a single chemical species. Statistical thermodynamics tools will be used to derive the perfect gas equation of state and equilibrium constant. We will just show the idea from first principles. Equilibrium composition of high temperature air will be discussed at the end, and to begin the discussion, we will also recapitulate very briefly about what we have tried covering in the previous lectures of week 6. Beginning with the revision part of week 6, you remember that in the first lecture we discussed about the different modes of energy that exist in a molecule, and we showed that in a quantized sense how the variation occurs at different levels for translational, rotational, vibrational as well as electronic forms of energy. And we saw that for translational form of energy, the different quantized energy levels are very close to each other, while for rotational they are further spaced and the spacing increases with energy level. Also, the jump from one level to the other are much larger than translational. Therefore, translational mode of energy almost looks like a continuous distribution, while rotational or other forms look very discrete. Vibrational energy jumps from one energy level to the other, they decrease with increasing energy, but the first jump itself is larger than rotational. For electronic energy, the jumps are similar to vibrational, but the first jump itself is very large, and these energy changes are extremely large compared to the other modes of energy. Again, we discussed that atoms can have only two possible forms of energy, translational and electronic, while molecules can have all four. Then we introduced the concept of macro states and micro states. So, we said that if the molecules are distributed over different energy levels, at each energy level again there are numerous energy states corresponding to each level. That is what is called as the statistical weight or degeneracy expressed by G I, and the macro states can change over time. They basically show you a population distribution, and due to the continuous molecular collisions, the population distribution can change from time to time. Of course, the total count of the number of molecules remains invariant. Then we introduced for a given macro state the possibility of different micro states, and then we considered the degeneracy aspect in the form of boxes or containers where molecules can be located, and then we said that in a certain form of particles we can only accommodate one molecule in one container, while in other we can accommodate more than one. That is what gave rise to the Fermi-Dirac and the Bose-Einstein statistics. We discussed that at length consequently, and then we took the discussion forward further, where we identified the most probable macro state where the largest number of possible micro states exist, we came up with the Boltzmann distribution of the population, introduced the partition function, and now in the previous lecture towards the end we had discussed about obtaining thermodynamic properties in terms of the partition function for a single chemical species, and thereby we were able to show how the thermodynamic properties become temperature dependent. And for each mode of energy showed the Q forms, the Q translational, the Q rotational, and so on, and using those forms by taking the partial derivative with respect to temperature for constant volume, we obtained the specific internal energy for the different energy modes for translational, rotational, vibrational, and electronic. We could not derive it explicitly because it depends on spectroscopic measurements, and then we wrote down the expressions for atoms as well as molecules. As mentioned before, atoms can have only 2 forms of energy while molecules can have 4, and we could see that temperature dependence in the CV expression shows up due to the contribution from the vibrational energy, which made it evident that from temperatures where vibrational energy gets excited, the CV will definitely become a function of temperature. That means, from a calorically perfect gas where the CV would be a constant, we would be moving to a condition where CV becomes a function of temperature. At still higher temperatures, chemical reactions take place and there are massive variations in CV. In this lecture, we primarily would be looking at the composition of air when you raise the temperature of air, when the constituent molecules may undergo dissociation, and at still higher temperatures they may undergo ionization and so on. So, to take that discussion forward, we make use of this plot where we represent CV by R along the y axis and the temperature across along the x axis, but it is in a kind of a logarithmic form, while the y axis is linear. And we have shown that at extremely low temperatures close to absolute 0, how gradually the different energy modes get excited to begin with. So, in the range 0 to 1 Kelvin, you see that translational mode is excited, and between 1 to 3 Kelvin, translational as well as rotational modes get excited. So, incrementally it is the rotational mode which gets excited over the 1 to 3 Kelvin range, and thereby in terms of CV by R, the ratio changes from 3 by 2 to 5 by 2. Remember that if we are to look at atoms in that condition, that the translational part would be there, but rotational part does not exist, and there is no question of exciting the rotational mode. It is only for molecules that such a change will come about. From 3 Kelvin to around 600 Kelvin or so, we find that only the translational and rotational modes remain excited, while from 600 Kelvin to around 2000 Kelvin, the translational, rotational as well as vibrational mode gets excited. And you remember that the vibrational mode would end up contributing to CV by R. The contribution will be temperature dependent, and therefore, you see the variation in this stretch, where as the temperature changes, the CV by R keeps changing. So, CV by R becomes variable. As a consequence, if CV becomes a function of temperature, so would be Cp and so would be gamma. So, these basically follow from the fact that the CV is now changing with temperature. Now, coming back to the temperature range of 3 Kelvin to 600 Kelvin or so, we find through simple calculations we can show that the gamma will come out to be 1.4. It is just because Gamma is basically defined as the ratio of Cp by Cv, and Cp can be obtained from Cv by adding R. So, you basically have to add the Cv, which is 5 by 2 R plus R, which gives you 7 by 2 R here, and therefore, the Cp by Cv basically becomes 7 by 2 R by 5 by 2 R, which is 7 by 5, and that is what gives you 1.4. So, that is basically the calculation. As you can understand that as you go beyond 600 Kelvin, you have to invoke this expression, which is never going to be a constant. It is going to change as the temperature changes. So, you have to first find out what the Cv is as a function of temperature, add R to that Cv to get Cp, and then take a ratio of Cp by Cv to get you the gamma, which obviously means that gamma will become a function of temperature. So, that is left as a small homework exercise for you to explore. We have shown this variation up to about 2000 Kelvin or so, and beyond that chemical reactions set in. We are going to discuss a little bit of that too in the subsequent slides, but that cannot be addressed very simply through equations of this form, what we have expressed for Cv, and there we would have to deal with the chemical reactions. Now, in the 3 Kelvin to 600 Kelvin range again, as we have mentioned earlier too, the calorically perfect gas assumption is valid, and most of the gas dynamic analysis that we see caters to this kind of behavior of the gas. But as you can understand that hypersonic hypervelocity flows will involve temperatures in this range and much beyond at times, and therefore, we have to gear up to deal with temperature dependency of thermodynamic properties. We have tried to sum up all the facts once again over here. Maybe we will spend a minute to go through this once again as a recapitulation. So, for very low temperatures of the order of 1 Kelvin, only translational mode is excited. Hence, for atoms as well as for molecules, Cv is 3 by 2 R, and it is assumed that the gas will not liquefy at low temperatures, which is of course a major issue. Normally, it would liquefy at much higher temperatures than that, but this is used as an assumption for simplicity. Rotational energy mode gets excited between 1 to 3 Kelvin, and thus the by the time you reach 3 Kelvin, you would if you recall, we already reached a value of 5 by 2 R, and between 3 Kelvin and 600 Kelvin, translational and rotational energy modes remain excited. And thus for atoms, the rotational energy does not exist, and therefore, Cv stays at 3 by 2 R, but for molecules it becomes 5 by 2 R. In this temperature range, the gas behaves as a calorically perfect one. Cp happens to be 7 by 2 R, therefore, gamma becomes 1.4, which is a constant, and it matches closely with gamma value of air at normal temperature. Above 600 Kelvin, vibrational energy mode gets excited, and therefore, Cv becomes a function of temperature for molecules. This again does not work for atoms, because there is no question of vibrational energy when you do not have 2 or more atoms involved in the gas. This variation continues till 2000 Kelvin, and beyond 2000 Kelvin chemical reactions would occur. Cv would start changing quite severely. This is another interesting pursuit. We are going to talk about the equation of state for a perfect gas for a while. We remember that it was postulated through experimental observations of some of the very notable scientists, in the previous few centuries, and that is what is discussed widely in classical thermodynamics. Those are the building blocks. While in statistical thermodynamics, it can be derived from first principles. So, there is no question of postulation from experimental observations, but rather you can build it up from basic principles. So, how do we do that? We again invoke the partition function. We basically use the pressure equation that we had derived in terms of the partition function. This is the equation that we have, and we just bring in the translational form of Q, because that is the one which has dependence on the volume of the thermodynamic system. That is the only one that depends on V. The others do not have a dependence on V. Therefore, only that would contribute to a derivative of this kind. The others will contribute 0 anyway. So, when you carry out the derivative, you end up getting a value of this, and when you substitute that on the right hand side of the pressure equation, you come up with this form, and finally, on rearrangement you get P V is equal to N K T, which is one of the forms of the equation of state of a perfect gas that we have discussed about from the point of view of classical thermodynamics. But interestingly, this is directly derivable in statistical thermodynamics. Again, the model of perfect gas, how it is embedded in the statistical thermodynamic scenario is that all the molecules that we consider are indistinguishable from each other. They do not influence each other to the extent that you have the effect of so called real gas, and therefore, the assumptions that we made when we discussed about perfect gas, when we were discussing it from the point of view of classical thermodynamics, they are also sustained when we derived it from first principles in the statistical thermodynamic sense. This is an interesting outcome. Another one which we will not try to elaborately discuss or prove, but we are just going to provide it as a result. So, when we consider chemically reacting species, we would need to invoke the equilibrium constant. Statistical thermodynamics can derive its expression from first principles again. The detailed derivation is something that we are not attempting here. We are just going to provide the final form. Of course, we consider a generic chemical reaction where the reactants on the left hand side are sent to the right, and the nu I being the stoichiometric mole numbers for all the species I, Ai being the chemical symbol for species I, and consequently nu I for reactants are going to be negative, for products are going to be positive. This we had learnt earlier too. And if you look at the final form of Kp as a function of temperature, then this is how it looks. It is of course a function of temperature alone. If you remember, when we had discussed it previously, we had sent the pressure to 1 atmosphere as a reference pressure, and therefore, the Kp had become a function of temperature alone. The same principle holds good here too. It is a product of all the partial pressures raised to their stoichiometric mole numbers, and in the statistical thermodynamics world, it would finally be represented in a form like this: Kt by V, the whole raised to sigma nu I. So, that sigma nu I is nothing but a summation of stoichiometric mole numbers with positive values for products and negative values for reactants. Then comes an exponential term, as is expected in equilibrium constant definitions. So, you see e to the power of minus delta epsilon naught by Kt, and then comes a pi term involving the partition functions. Before we move on to the partition function part, the delta epsilon naught is basically a difference of 0 point energy between the products and the reactants. since the reactants have moved over to the right hand side, therefore their signs have become negative. Effectively, it also influences the delta epsilon naught calculation, and you find it as a difference. And then finally, the pi terms, the product terms of the partition functions for individual species raised to their respective stoichiometric mole numbers. Here again, as you can see, partition function plays a pivotal role in describing the equilibrium constant or deciding its value. So, this of course, we are not dealing with it in detail, we are just providing it as a fact. With this, we move on to the last discussion that we have now. So, a few general points about equilibrium composition of high temperature air. When air is heated in the temperature range of about 2500 Kelvin to around 9000 Kelvin, the chemical reactions would occur between molecular oxygen and nitrogen, leading to formation of various species, and the consequent mixture would therefore comprise of these species. Beyond 9000 Kelvin, there would be ionization of atomic oxygen and nitrogen as well. So, we are not going into that temperature range. So, here you see O2, N2, O, N, NO, NO plus and E minus are the species that we are talking about. If the reacting gas mixture has a stable temperature and pressure, and it gets long enough time such that the chemical reactions are occurring an equal amount in both the forward and reverse directions, then chemical equilibrium would be attained. At a given temperature and pressure, specific fixed amounts of the above species would constitute the gas mixture. That means, the partial pressures of the individual species will get fixed at the equilibrium condition. From statistical thermodynamics point of view, the system would attain chemical equilibrium when maximum number of microstates are formed. That means, W max corresponds to chemical equilibrium when we discuss from the statistical thermodynamics point of view. In an equilibrium chemically reacting gas mixture, the gas particles of each individual species are distributed over their respective energy levels according to the Boltzmann distribution. So, that is again from the statistical thermodynamics point of view, that gives you the population distribution, that gives you the macro state, the most probable macro state. The important chemical reactions in this temperature range, we have mentioned 4 of them. There is of course a reason, a justification behind only mentioning 4 equations. We will talk about it a little later. So, we are talking about dissociation of molecular oxygen and nitrogen. We are talking about combination of N and O to form NO, and then again formation of NO plus and free electrons. Let the partial pressures of the 7 different species that we have mentioned about, which get formed in the process, be represented with lowercase p with respective subscripts. We are familiar with this nomenclature already. We have learnt about the Dalton's law too in previous lectures. So, we are going to need all that knowledge here once again. The composition of the gas mixture at the certain temperature and pressure can be obtained only if these partial pressures are obtained. Obtained of course through a solution procedure. So, we are going to look at the equations which need to be solved simultaneously to come to the values of the respective partial pressures. And as we said, we need to invoke the Dalton's law of partial pressure. So, pressure has to be provided as an input, the pressure in the sense the total pressure of the gas mixture, that has to come from a separate input. It has to be pre-specified, and then we will find that that is basically comprised of summation of all these partial pressures according to Dalton's law of partial pressures. That is the first equation that we are including in the system. Then comes the equilibrium constants for the 4 different chemical reactions that we have shown in the previous slide, and the KPT expressions for each one of the chemical reactions would be obtained based on statistical thermodynamics principles, or they may be obtained from Janov tables. If we are using statistical thermodynamics, then these are the forms we have to use, which we discussed in the previous slides, and partition functions of individual species have to be brought into the picture. Thereby, from the first chemical reaction equation, you will get this form involving KpO2 involving the oxygen dissociation. Then the second equation for nitrogen dissociation, the equation for formation of NO, and the equation for formation of NO plus and electrons. So, these are the 4 chemical reactions that we are bringing into the respective equilibrium constants. So, we have now got 5 equations followed by the mass balance equation, where we have the ratio of the number of oxygen and nitrogen nuclei at the beginning of the reactions. Let us say from the original air mixture, which was at a lower temperature, we already knew that normally it comes to about 0.25, and here it has been represented in terms of ratio of sum of partial pressures of those species which include either oxygen or nitrogen, depending on the situation, whether it is in the numerator or it is in the denominator. This is the 6th equation, and finally equation dealing with electric charge conservation, where we involve eta NO plus and equate it with eta E minus in terms of partial pressure. This is what the condition is. That gives you the 7th equation. Finally, we have 7 non-linear simultaneous algebraic equations to be solved in order to obtain the 7 unknown partial pressures. The rule is that if there are sp number of species, any number of elements, then we need sp minus any number of independent chemical equations. The word independent again is very important. We should not get any chemical equation in that set by a combination of others. For high temperature reacting air, we found that sp happens to be 7. There are 7 species. The number of elements are namely On and E minus, which is 3 in number. Therefore, the difference gives us 4, which should be the number of independent chemical reactions which can be considered. Based on that, we have chosen 4 very important vital chemical equations only, which represent the system. In a previous lecture, you remember we had discussed about this fact that over a certain temperature range spanning from very low, close to absolute 0 to about 9000 Kelvin, how air reacts when you have 1 atm pressure. These temperatures get massively altered if you change the pressure significantly. Thereby, we talked about excitation of the different energy modes. We talked about dissociation of oxygen, dissociation of nitrogen. We showed that oxygen begins to dissociate at 2000, that ends by about 4000, N2 starts dissociating at 4000 or so, and it gets completed by about 9000 or so. Beyond 9000 is the ionization range, where atomic nitrogen and oxygen get ionized into N plus and O plus and releasing free electrons. Those were the details we had already discussed about earlier. So, keeping that information in mind, we finally come to a plot where we see that for 1 atm pressure, if we vary the temperature over that range of about 2000 to 9000 Kelvin or so, this is how we expect the things to change. And we are just showing the trends over here. You see gradually with increase in temperature, the molecular oxygen and nitrogen mole fractions reduce. The mole fractions for atomic oxygen and nitrogen increase. Again, they recombine to form NO. NO mole fraction peaks at about 3500 Kelvin or so. And again, keep in mind that specifying the pressure is a very important thing to do over here. If pressure was increased substantially, then all the species mole fraction variation curves would shift towards the right. So, all these curves would move towards the right with pressure increase. That means the dissipation processes would be delayed to higher temperatures when you increase the pressure. Just the opposite happens if pressure is reduced. All these curves will move to lower temperatures. And we think it is a good point to end the week 6 discussions here. In this lecture, we discussed about variation of Cv as a function of temperature and pressure for a single chemical species. Statistical thermodynamics was used to derive the perfect gas equation of state, and equilibrium constant expression was discussed, and these were done from first principles. Finally, we ended the discussion by looking at equilibrium composition of high temperature air. In this lecture, in the beginning, we also had a brief recapitulations of many of the fundamentals which were discussed in the previous lectures of this week. Thank you.